Now, you'll also notice here that instead of typing descending as capital DESC, I typed it lowercase. SQL is one of the few languages still in use, Fortran is the other, that is case insensitive. I could type this as select last name from person where login in school and mlom. The data itself is case sensitive. Uppercase and lowercase matter. But the commands and keywords, the column names and table names can be written in any arbitrary mix. Please do not do this. Right? It makes things very hard to read. Lots of studies have been done on readability of text. It doesn't matter what rules you follow as long as you are consistent. If you're consistent, readers' brains get a chance to get used to reading things a certain way. They recognize the shape of the word and they read over it quickly. If you mix in case like from, person, like this, or upper and lower login, like that, it's really hard for people to read that. They have to stop and consider each letter because it's an unfamiliar pattern. So please, don't do this. All right, we've now got a way to select particular rows. Let's take a look at the experiment table. I would like to get all of the experiments that actually took a positive number of hours, because if you look at the hours column, you can see that 2 of the experiments have negative numbers for the hours. Project ID 1737, oh, that's the time travel experiment. Must be going well. This is what passes for humor among programmers. So, we want to filter those out and only keep the experiments that have a positive number of hours, because that's all we can bill back to the funding agency. If we try to bill back negative hours, they're going to expect money from us, and clearly we don't want to do that. So, let's start by saying select star from experiment. Okay, that's all of the data we've got. Yep, the column's called hours, so select star from experiment where hours is greater than or equal to 0. So I don't just test on equality. Here I'm saying get the value of the hours column for each record and check to see where that is greater than or equal to 0, and those are the only records I want to keep. All right, that worked pretty well. I've got 1, 2, 3, 4 columns. Switch back to the diagram. 1, 2, 3, 4 columns have positive hours. And if I say where hour is less than 0, I get the other 2 records. There are 6 records in total in the table, 2 for each experiment, 2 for each project. So if I select hours greater than or equal to 0, that gets me 4 of them. If I select hours less than 0, that gets me 2, because every number is either greater than or equal to 0, or it's less than 0. It's the law of the excluded middle. Well, everything's going fine until I say, let's get all the experiments that were run in either the 20th century or the 19th century. So we're going to be selecting experiment date. Well, the experiment dates are values like 1900-07-05. So let's say, select star from experiment, where experiment date greater than or equal to 1900-00-00. It's a non-existent date that is greater than anything in the 19th century, but less than anything in the 20th century. Okay, that got me 2 records. There were 2 experiments conducted in the 20th century. Let's go back and rerun this and select less than. I have 6 records in my database. The first query got 2, so if I invert the test, I should get 4. But I only get 3. That's weird. According to this, 2 records have dates greater than or equal to 1900-00. 3 have less, but there are 6 records in total. Where's my missing record? Well, if you take a look at the diagram again, you'll notice that the very first experiment doesn't have an actual date under experiment date. It has a special value called null. And this is one of the things that is both useful and infuriating about relational database systems. You're used to a system where things are either true or false, 2-valued logic. Databases work with 3-valued logic. There's true, there's false, and there's I don't know. Because there are often holes in real-world data. And rather than filling in some arbitrary value, the database systems actually allow you to say, I don't have a value here. And you do that by putting in the special marker null. Null is not less than 0. If I say select null less than 0, the answer is null. If I say select null greater than or equal to 0, the answer is also null. Null is not less than 0, because if we don't know the value, we don't know if it's less than 0. In fact, null less than 0 returns null. It doesn't return true or false. Null greater than or equal to 0 returns null rather than true or false. Null plus 5 is null. Null minus 15.3 is null. Null and anything is null, because as soon as you've got an unknown in an equation or a relationship, the answer is unknown. So, when I say, let's select everything where the experiment date is greater than or equal to 1900, there are 2 cases where I know the answer, and it's true. There are 3 cases where I know the answer and it's false, and there's 1 case where I don't know the answer because the input value is null, so it doesn't show up in my output. Similarly, when I select experiments where the date is less than 1900-0-0, there are 3 cases where that test is true, 2 where it's false, and 1 where it's null, because I don't know the experiment date. In fact, the only thing you can safely do with null is say, select star from experiment where experiment date is null. And you can equally well say is not null. Those are the only 2 operations, is null and is not null, that are safe to do with nulls. This is not the database's fault. Real-world data is often missing information. You may have somebody where you have the year of their birth, but not the month of the day. I, in fact, have family members going back a couple of generations where we're not sure of the year. We know the month and day, but we don't know what the year was. Was it 1855, 56, or 57? You may have people that don't have an address. For example, if you are studying the spread of drug-resistant tuberculosis, you've got patient data, but you're not allowed to know the details about the patient. In particular, you're not allowed to know their address for privacy reasons. The most you'll get is the postcode. Here's a patient at a hospital. Did they test positive for drug-resistant tuberculosis, and what's the postal code of their home address? Right? Over here, you have census data. What it will tell you is average income per postcode. So you're trying to see, is there a correlation between poverty and the spread of drug-resistant tuberculosis? Well, the very first time I tried to solve this problem, I got it wrong. My SQL query and my statistics said there was no correlation. What had happened was, I'm selecting everybody by postcode and matching it with the income by postcode, but all of those people that don't have an address are being thrown away because the address field is null. Who doesn't have an address? Homeless people. If you take the homeless people out of your sample population, lo and behold, you don't see any correlation between regional income and the spread of drug-resistant tuberculosis. That's because you've thrown away one of the major contributors, which is people living on the street. One mistake in a database query skewed my statistics. That's no different from having a piece of experimental apparatus that has a systematic flaw in it. An oscilloscope that consistently registers voltage high, a telescope that has chromatic aberration, and so forth. We treat it exactly the same way. Now, once you've realized the problem, it stops being a computing problem and it starts being a scientific or statistical problem. Do you assume an income or model an income for people without a home address? Do you treat them as a separate population and just do 2 sets of statistics? This isn't something that the program can answer, but you have to take your answer into account when you're writing the program. So, I've now got a way to select out people, projects, and other things out of this data based on the values in the columns. What I don't yet have is a way to connect values from different tables. For example, the project table gives me the project ID and the project name. The experiment table gives me a project ID, the date, and the hours. What I want for reporting purposes is the name, the date, and the hours. Not the project ID, because the number 1709 is not going to make any sense to the university accounting department. What they want is the project name, teleportation, and then the experiment date and the number of hours. So somehow I have to join information from two tables together. Okay. In order to do that, I'm going to have to jump through a couple of hoops. Once we've done the jumping, you'll understand why. Here's the first thing I'm going to say. Select star from project, join, experiment. The join operation in SQL creates the cross product. Every single row from one table is concatenated with every single row from the other table. All possible combinations. So if we look at the diagram again, there are 3 rows in the project table. There are 6 rows in the experiment table. So there should be 18 rows of output, because 3 times 6 is 18. The first row of project is being joined with the first, second, third, fourth, fifth, and sixth rows of experiment. Then the second row of project is being joined with each of those rows, and then the third row is being joined with each of those rows. So I get all possible combinations of rows, and the output will have 2 columns from project, 5 columns from experiment, for a total of 7 columns. Because as my 5-year-old daughter will tell you, 2 plus 5 is 7. So if I take a look at this data, I've got 1, 2, 3, 4, 5, 6, 7 columns, and yes, if you count them, there are 18 rows. So now I've got all possible combinations of information from the 2 tables to work with. What I have to do is add some where clauses to throw away the information that I don't want. Well, when I'm joining these, the only combinations that make sense are the ones that have the same project ID. If I have a row that has the project ID 1214 from the project table, but the project ID 1737 from the experiment table, that row in the result has some information about anti-gravity and some information about time travel. So for our present purposes, it's not useful. So I want to select star from project join experiment, where project ID is equal to experiment project ID. Now notice the notation. It's table.column name. Because, again, looking at the diagram, my output has 2 columns called project ID. One came from the project table, one came from the experiment table. Every table name has to be unique, and every column name has to be unique within the table. But I can have columns in different tables with the same names. In fact, I also have a project ID column in the involved table, which also has an experiment ID table, which also shows up in experiment. And I've got a login column in involved. There's also a login column in person. So I can have the same column name appearing in many different places. I therefore need to say table name dot column name to tell you which of those 2 possibilities I'm talking about. Am I talking about the one I got from project or the one I got from experiment? Here in my query, I'm saying that the only rows I'm going to keep are the ones where the project ID from the project table matches the project ID from the experiment table, because if they're different, the bits of information I joined are about different projects. Okay, let's run that. And lo and behold, I'm down to 6 rows. And each of those rows has 2 columns that it got from the project table, followed by 5 columns that it got from the experiment table. And the project IDs are the same. The information from the project table is about the same project that the experiment table is talking about, because the 2 experiment IDs are the same. So now I can change my query to be select project name experiment.hours from project, I'll try to be consistent with my capitalization, join experiment, where project ID is the same as experiment project ID. Here's how you read this query. We start at the middle and work our way out. I'm joining the project and experiment tables. That's the very first thing I conceptually do, is take all possible combinations of information from project with information from experiment. That gives me all of the possibilities I might want. That's step 1. Step 2 is filter the rows in that cross product and only keep the ones that pass this test. And in this case, the test is that they're talking about the same project. They've got the same project ID coming from both sources, because if the project IDs are different, I've got information about two different projects in one row, and right now that's not useful. So, do the join, then do the filtering based on the properties in the matchup, and then decide what to display. And there we go. There's the project name and the hours on each of its experiments. That's what I wanted, and I got it by joining information from two tables. This is why you often see serial numbers assigned to things. You will have a healthcare number, you'll have a social insurance or social security number, you'll have a university student number, and so forth. Those numbers are almost always keys in a database table somewhere, something like the project ID. The reason you don't use things like names as keys is, number one, a lot of people have the same name. There are a lot of other Greg Wilsons in the world. Number two, those values can change. We might want to rename the anti-gravity project. We might want to rename time travel, but we don't want to lose all of the historical information. So if we have an arbitrary identifier that is internal to the database system, that uniquely identifies the thing, we can change all of the other aspects like name, address, age, and so forth, and still be sure that we're talking about the same entity. So, the SQL you have seen now accounts for well over half of the queries you will ever write. You can take information from several tables, join it up, filter out the stuff you don't want, and then keep only the columns that are useful for the next stage in your processing. So, let's try to make this a little more efficient.